today's the first day of our stellar science badge. So now we were talking mostly about planets and our solar system. Now we'll be moving into talking more about stars, both our sun, which we'll get into next week, and then also other stars and how we can learn about them. Before we can really dig into stars, though, we have to think about what we know about light. So with the planets in our solar system, there were some missions, some space missions where we've gotten data by actually going to those planets. The only star that's close enough for us to get to is the sun. Any other star is too far away. We haven't sent anything to it. I think there's been, like I said, there's a few probes that have been to the sun, most recently the Parker Solar Probe. But any other star, all of the information we're getting about that star is just from the light it emits. The closest star to us outside of the sun is about 4 light years away. So if we could travel at the speed of light, which we can't at the moment, it would take us 4 years to get there. So right now, and kind of for the foreseeable future, everything we know about stars has to come through the light that they emit and then reaches us. Which means in order to understand what astronomers know about stars, we have to first really understand what astronomers know about light. So we do a lot of tests here on Earth where we can control the environment, we can be really sure what's going on, so we really know what's happening with light. And then we take that information and we go out and we look at stars and see how the light from stars changes, and just figure out a lot of different things that we can learn about those stars with only this information from light. So today is going to be a little heavy on the physics, a little bit more on that side, and then we'll get back next week. We'll start talking about the sun and more fun astronomy-based things, less physics and math, more astronomy and that kind of thing. So essentially, this is what I just said. Today we're going to focus on the physics of light and how we know what we know about light, and then we'll get into stars. So the first question that we have to ask is, what actually is light? And this is a big problem because we don't really completely understand light just in general. And I don't think as humans we have a way of completely conceptualizing what light is, because it's somewhere between the kind of things that we interact with in the world on a day-to-day basis. So a lot of times you might hear that light is either a particle or a wave. And so this is kind of how we're going to think about light. It's probably actually somehow somewhere between those two things. We don't completely understand what that means, and I don't think we have a way to do that. If you can imagine a basketball somehow becoming like a pressure wave in air and then going back to being a basketball, then maybe you can understand light. I can't understand how that might be possible, but that's what light seems to be doing. Light is both an electromagnetic wave and a stream of particles that we call photons. So what does that mean and how do we know that? So the first thing we can think about is we know that light acts like a wave because of how it interferes with itself. So we can get both constructive and destructive interference. And I want to go forward just really quickly because the way we normally think about waves is we can think about waves in water. So this is just going to show what constructive and destructive interference is going to look like. Maybe, hopefully.
I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is...
So what I really want you to see here is that when we have 2 sources of waves, there are places where those waves are really strong, like right in here. Hopefully you can see my cursor. Go ahead and try. So right here, we can see there's really a strong peak in the wave where these two waves are interfering to create a larger wave. And here we can see those two waves are interfering, adding up to create almost no wave at all. So when we have two waves, they can interfere with each other and either add up to be an even bigger wave or decrease to be a smaller wave. Particles won't do this. Particles, you can only add them together. You can't get particles slamming together and killing and annihilating each other. Not the same kind of particle. So if we see these kind of patterns where there's a bright spot and then a dim spot and then a bright spot and then a dim spot when we have two light sources interacting, that will tell us that light is acting as a wave. And that's what we see when we do the double slit experiment. So here we have one light source and it's passing through two slits in a wall. And what happens is as it comes out, you get places where there's positive interference. So there's really bright spots and there's negative interference where there's almost no light. So this is a really famous experiment that was first done to show that light must be acting as a wave. Light interferes with itself. We get places where it's really bright and places where the light can add up to be something brighter, but also places where the light can cancel itself out and get dimmer. So light must be a wave. What's important about this is it means that light has a wavelength. We will get into what that means, but light also has a wavelength, a frequency, and a speed. Which if it was a particle, you can't really think of the wavelength of a particle. That doesn't 100% make sense. So that's light acting like a wave. We've done it. There is an experiment that shows that it must be semi-wavelength, but we can also see there are times when light acts like a particle. So we can think of a particle as like proton or electron if you've taken chemistry. It's also just like a ball, essentially, just a really, really, really small massless ball of light. So kind of weird to think about. But these particles called photons, we know they must exist because when you shoot light at certain metals, it can hit those metals and kick off an electron. And if it was a wave, we wouldn't really expect that. We need particles to bump into the atoms in a metal block that will actually kick off electrons. So this is something called the photoelectric effect. And it's actually how any camera you use works. So when you take a picture with your cell phone, what's happening is the shutter on your cell phone camera is opening briefly, letting light in. Light's coming in and hitting a chip, a camera chip, and it's kicking off electrons. And your phone is able to measure how many electrons got kicked off while it was open, and that tells it how bright different parts of your image should look. So next time you post something on Instagram, you can think about how the photoelectric effect allows you to do that. So if light wasn't acting like a particle, we wouldn't be able to take pictures the way we do. If light was only a wave, we wouldn't be able, cameras wouldn't exist. If you wanted a selfie, you'd have to get someone to paint you. But light does act as a particle. There is the photoelectric effect. So we know light must be both wave-like and particle-like, which is weird, but it's just how light is. I don't expect that to really make sense. It doesn't make sense to me. The important things to take away from this is that light is both a particle and a wave. Light has a wavelength and a frequency because it's like a wave. Light also has an energy because it's like a particle. The other thing we need to think about when we consider what light is that a lot of times when we think about light as just normal humans, what we're talking about is a really small part of the electromagnetic spectrum, this little bit here that is visible light. So let me grab this again. It's probably not a good color. So right in here, this is where there is visible light. This is all the light we can see is light with a wavelength between about 400 nanometers to 700 nanometers. So that's blue is going to be 400 nanometers and red is going to be about 700 nanometers. So this is light with wavelengths about the size of a virus or a bacteria is everything that we can see. To an astronomer, though, that's leaving out a ton of light, a ton of information, because that's only looking at a really small part of the electromagnetic spectrum. Light can have all kinds of wavelengths outside of this little realm that we are able to see. And we want to measure those as well, because we want to get as much information out of these stars, out of starlight, as we possibly can. So we think, so light is really any part of the electromagnetic spectrum, any kind of electromagnetic radiation, I'm going to call light, even though a lot of this is not what we see, not what we might think of. So at really long wavelengths, there's radio waves. Radio waves, again, really long wavelength light. So this is getting light with a wavelength that might be bigger than a house. But it's still something we can measure with telescopes, something we can take pictures of galaxies and stars. We can look in the radio waves and we can learn more about what's happening there. Microwaves are another form of light, so this is getting slightly shorter. Light waves that are around the size of your fingernail are going to be microwaves, just another form of light. And then there's infrared. So infrared is going to be anything that emits, anything that has a temperature, anything that's slightly warm is going to emit infrared light. If we could see infrared, we would see that we are all glowing in the infrared because we have a temperature. So if you've had to go in somewhere and they've scanned your forehead using one of the thermometers now that don't go in your mouth, what it's doing is it's looking at how bright you are in the infrared, and it's using that to figure out what your temperature is. So that's a way that we're using light in our day-to-day life now that we weren't before the pandemic. So those are all wavelengths that are longer than what we can see. There's also wavelengths that are shorter than we can see. So that's going to be things like ultraviolet light. So if you've seen black lights, those have higher UV light. So very short, we're getting shorter wavelengths. The sun puts out a lot of UV light. But a lot of that gets blocked by our atmosphere, which is great. And then there's X-ray and gamma ray light. So even though rays you might think are something different, it's still light. X-rays are still light, gamma rays are still light. And these are all in the astronomer's toolbox for ways that we can look at stars and galaxies and learn things about them, despite the fact we cannot go there. So what we know so far, light is both a particle and a wave. That means it has a wavelength, a frequency, and an energy. And those wavelengths don't just cover what we can see, they span the entire electromagnetic spectrum, starting in radio waves and going all the way up to the very short wave, long wavelength radio waves going to very short wavelength gamma rays. So with that, we can kind of put some of this together and start thinking about the relationship between these properties of the particle and the properties of a wave. So high energy photons, high energy particles are going to correspond to shorter wavelengths and high frequencies. So high energy, high frequency, small wavelength, very short, very small wavelength. This is going to be blue light, UV light, and then also the X-ray and gamma ray light. Low energy photons, so lower energy, is going to be lower frequency, so low in frequency, but it's going to be longer or larger wavelength. So radio wave, microwave light is going to be lower energy, longer wavelength, smaller frequency. And then we can determine the energy from the wavelength or the frequency using these equations here. So energy is equal to a constant h called Planck's constant times frequency, which is usually represented by the Greek letter nu. And frequency is how many waves are happening per second. So should have said that earlier, sorry. Frequency is just how often is a peak in wavelength going by you. So the frequency of an ocean wave, if you're standing, every time you would kind of bounce in the ocean, that would be the time between those separations would tell you the frequency. We can also find energy using hc divided by lambda. Lambda represents wavelength. So longer, bigger wavelength, lower energy, that's why we divide. So, and c, sorry, is our speed of light. So h is a constant, c is a constant, and then we divide by our wavelength to find energy. So that's going to be the relationship between the energy, the frequency, and the wavelength. We also know that all light travels at the speed of light, which is 3 times 10 to the 8th meters per second, or 6.7 times 10 to the 8 miles per hour. So 670 million miles per hour approximately. So very, very, very fast. Nothing goes faster than the speed of light, but that does mean that we're semi-limited. So all light travels to us, it takes time to get here. So when you look at the moon is about 1.3 light seconds away, which means it takes light 1.3 seconds to travel from the moon to us. So we're seeing the moon as it was 1.3 seconds ago. The sun is about 8 light minutes away. So light takes 8 minutes to travel from the sun to us. And so we see the sun as it was 8 minutes ago. The nearest star was 4 light years. So we see that star as it was 4 years ago. If that star died, we wouldn't know for 4 years. So I just threw a lot of information. Does anyone have any questions before we learn how we measure the speed of light?
I have a question about starlight. When you said that if a star dies and it's like 4 years away, we don't know about it until the light stops reaching us in 4 years. Is there a way to look at a planet or a star in the sky that we can see and say, okay, that star has already died and we're gonna stop seeing it in 8 years?
That's a good question. I'm sort of yes and no. We'll talk about this soon, but we can predict how long stars will live. So if we look in the sky and we say, there's a star, we can figure out if we can figure out how far away the star is, and we can say that star is 100 million light years away. But I know that kind of star only lives for 10 million years. I can be pretty guaranteed that it's dead, but I'm still gonna see it for anywhere between 1 and 90 million years. So it's hard to say exactly, but there are other signs. There's a star Betelgeuse, which is a really bright red star in our sky that has started pulsating, which tells us it's going to die soon, which means it is probably already dead, but we can still see it because the light from its death hasn't reached us yet. So there are some indications that a star will die soon, and that might indicate that the star has died, and what we are seeing is the last few years or 100 years before we actually see the star's death. So it's a little wishy-washy answer, but kind of yes and no.
Thank you.
Yeah. Any other questions? So we're going to take a little bit to learn about how we measure the speed of light. And unfortunately, or fortunately, depending on how you feel, you can't buy Peeps right now because the Peeps manufacturing has stopped. So no Peeps, but you can still do this with any kind of marshmallows if you want to measure the speed of light.
It's the week after Easter, and that means homes all across America are overflowing with stale Peeps. Now, you could either eat those Peeps, or you could use them to find the speed of light.
Finding the speed of light with Peeps.
The speed of light is one of those numbers that people have chased for centuries. Galileo wanted to know how fast light moves,
Buonasera.
so he proposed an experiment.
Facciamolo.
He would uncover a lantern, and when the light reached his assistant, the assistant would quickly uncover his own lantern. Using a water clock, Galileo would keep track of the time between uncovering his light and seeing his assistant's light. Up close, there was no noticeable delay except for the split second it took his assistant to react. Then they started moving away from each other. Galileo figured the delay would get longer and longer because the light would need more time to travel the greater distance. But even when they were a mile apart, there wasn't a noticeable pause.
Che rabbia.
He couldn't have guessed that light had made that trip in 100,000th of a second. Centuries later, in 1849, a French scientist, whose name I can't pronounce,
Armand Hippolyte Louis Fizeau.
came up with an even better way to measure the speed of light, which was pretty impressive considering that people weren't even using light bulbs yet. He took a toothed wheel and spun it faster and faster. He shot a beam of light between the teeth and reflected that beam of light off a mere 5 miles away. By the time the light got back, a tiny fraction of a second later, the teeth had moved over just enough to block the light. No light made it back through. But if he made the wheel spin a little faster, the teeth would move over one whole position and the light could get through. So when
Fizeau.
he saw the light, he knew the wheel was spinning so fast that a single tooth was moving over one place in the time it took light to travel 10 miles. With some quick math,
Armand Hippolyte Louis Fizeau.
determined that the speed of light was 700 million miles per hour, which we now know was only 5% off the actual value. Today, I can find the speed of light in my kitchen, and that brings us back to Peeps
Finding the speed of light with Peeps.
and a microwave,
And a microwave.
and just a little bit of physics.
And physics. Just a little bit.
Microwaves travel at the speed of light. And like all waves, their speed is determined by how fast they go up and down, that's the frequency, and their wavelength. Frequency is written on the side of my microwave right here, 2,450 megahertz. So we've got the frequency. Now to calculate the speed, we just need to know the wavelength. And we can find the wavelength by microwaving Peeps. I'll set it on low so the Peeps don't just explode. Let it run for a minute or two. Inside, microwaves are bouncing around. In some spots, there isn't much energy at all. And Peeps in those areas stay cold. In other spots, there's lots of energy and the Peeps get really hot. Those hot spots are half a wavelength apart. So in theory, if I measure the distance between melted Peeps, I can find the wavelength. And sure enough, some of the Peeps are really gooey, while others haven't melted at all. Poking around, I found a rough location for a handful of hot spots, and I measured the distance between them. Those average out to 2.43 inches, so that's half a wavelength. Multiply by 2, and we get a wavelength of 4.86 inches. So now, to find the speed of the microwaves, which, remember, is the speed of light, I just have to do the math. Frequency times wavelength, 2,450 megahertz times 4.86 inches gives us about 12 billion inches per second, or 676 million miles per hour. And that's pretty close to the actual speed of light.
We just found speed of light with Peeps.
So there you go. A little bit about the history of how The speed of light was initially found using that Fizeau's experiment where he looked to see how fast he would need to spin a wheel to block light when it moved 10 miles, and then also how fast you'd have to spin it so you could see the light after it had moved 10 miles. And now we can use microwaves and marshmallows to find out if you have a specific frequency and a specific wavelength that you can measure based on where you're getting those interference points of positive interference where the waves add up and you get melted peeps, and where the waves cancel each other out and you get cold peeps, and you can find the wavelength using that. And then the velocity is going to be frequency times wavelength, and that's going to give you the speed of light. So if you do end up with a lot of marshmallows at some point and you want to try this, send me a picture. It's fun. But that's just a little history of how the speed of light was initially calculated, and how we do know that it's about 670 million miles per hour, or 3 times 10 to the 8th meters per second. Okay, so there's some physics of light. We know a bit about how it travels, how it has a wavelength and an energy because it's both a particle and a wave. Now we can start to think about what we can use that information, what we can use these physical concepts about light to start understanding stars. So the first thing we can potentially learn using light is to figure out how far away something is. And so if we think about this, like if you're driving at night and you see headlights coming towards you, you know how bright a car's headlights are. So you can estimate how far away that car is based on how bright the headlights look. As they get closer, they'll get brighter. As if they're really far away, they'll be pretty dim. So if we know how bright a star is, we can use how bright it looks to figure out how far away it is. Yeah. And in order to actually do this, we need to use something called the inverse square law, which tells us that the intensity of light is equal to 1 over distance squared. So as you get further away, as your distance gets larger, the light source is going to get dimmer as 1 over the square root of the square, 1 over that distance square, sorry, not square root, 1 over that distance squared. So if the car's headlights were 2 times as far away, they would be 1 over 2 squared, or 1/4 as bright as if they were maybe 1 car length in front of you. So you can figure out relative brightnesses, you can figure out distances using relative brightnesses. So light can tell us some information about how far away things are. The reason light falls off as 1 over d squared is because as you get further away, the light is being spread out over a bigger area. So that's why there's this distance squared. When you're really close, it's just covering a small area. As you get further and further away, that same light is covering a larger area, which makes it less intense which makes it less intense, sorry. So it looks dimmer. So this is showing at a distance of 1, the brightness equals 1. These are just arbitrary units. But at a distance of 2, the brightness is going to look as quarter as bright, and as a distance of 4, it's going to look 1 over 4 squared, or 1/16 as bright. I'll also point out there's a lab that should be available now. One of our first Stellar Badge labs will let you actually measure this. So just using a smartphone and a light source, you might be, there will be some error, but there's a way you can find the inverse square law is actually true. So if that's something you'd like to do, that's one of the labs that is now available. So how does this help us with stars? If, and this is where things get really iffy, if we know how bright a star is intrinsically, so if we know how bright the star would look if it was where our sun is, if we know exactly how bright the star is, and we know how bright the star looks, we can figure out how far away it is. So we haven't talked about this unit. There's a unit called a parsec, which is just a unit of distance. So 10 parsecs is just, it's about 30 light years away, just a distance. If there was a star that was 10 parsecs away and we detected 100 photons from it, if it was twice as far away, we would expect to see 1/2 squared, or 1/4 as many photons. So we would see 25 photons if it was 20 parsecs away, if we're seeing 100 photons when it's 10 parsecs away. So if we know how bright a star is, and we know how bright a star looks, we can use the differences between those to figure out how far away the star must be with this 1/d². So brightness goes as 1/d². So now we're going to test that out. If there was a star that we know has the same brightness as our sun, but it looks 10 million times fainter than our sun. So it appears 10 million times fainter. We want to know the distance. So our sun is 1 AU away. If 1/d² is 1/10 million, what is this? How 10 million? Yes, 1/d² is 1/10 million. How far away is this star? Got 3 people, or 7 people, sorry. About 1/3 of the class. I know you're all at computers, so you can use Google or Wolfram Alpha to plug these numbers in. I don't expect you to do this in your head. Almost half of folks. Cool, I'm gonna stop that share. Most of us got it right. So it's that 9.99 times 10 to the -6 meters, or 9.99 microns. So this is going to be an infrared light. So if we could see in the infrared, Earth would be glowing because it has a temperature. We can't, but if we could. So it's just the same thing. We would just take this equation here, 2.89 times 10 to the -3rd, and divide by 290. And what you should get is 9.99 times 10 to the -6 meters. Our kelvins will cancel and we'll be left with meters. Does anyone have any questions about how we got that? Okay. So we can potentially measure how far away a star is based on how bright it looks, if we know how bright it is. We can use Wien's law to measure the temperature of a star, if we can measure the peak wavelength. We can also use light to try to figure out what something is made out of. So you can think we kind of do this every day. If you look at something, you can see the color and you kind of can guess what it is. So grass has a different color than concrete, and you are using that color to figure out how the different properties of the material in your brain. Astronomers do this to figure out the surfaces of other planets. So like when we looked at the surface of Pluto last week, we saw that it had some red rocks covering its surface. Those reds were the same color as tholins on Earth. So astronomers were able to guess without actually landing anything on Pluto, that Pluto's surface has some of these tholins on it. So using color, we can figure out what something is made out of just based on what color it is. So light radiated, that's how we see color, is it's coming to us in light, so we can use that to find composition. Besides just kind of big overall colors, we can look at individual wavelengths as well. So this is where we're going to get to this spectra idea, where if we can break up light, we can squeeze out all the information about how bright it is at every different wavelength, every different color. We can really learn a lot about those light sources. So spectra is just bending light to see how bright it is at different colors. So if you've ever played with a prism, or if you've seen a rainbow, you've seen a spectra. You've seen the solar spectra. So what it is as light passes through a material like the glass in a spectra or the water in a rainstorm, that light gets bent as a function of wavelength. So different wavelengths exit the prism or the diffraction grating or the water droplet at a slightly different angle. So the light gets spread out as a function of wavelength. So we can use this to measure how bright a light source is at every individual wavelength. So this is extremely useful if we want to figure out what elements are present in the surface of a star. We can look at how bright that starlight is at every different wavelength, and we can use those brightnesses to start searching for different elements. So this is a really powerful tool. Astronomers use spectra to learn all kinds of things, and we're going to get to do that too. So I'm going to take, before we get to our activity, which will probably take most of the rest of class, I want to just really briefly say that I did mail out your lab equipment. One of the things in the lab equipment is going to look, I don't actually have one with me, I should have, but it's going to look sort of like this. It's going to look like a cardboard thing with a plastic film going through it, and that's a diffraction grating. What a diffraction grating does is exactly what a prism would do. It breaks up light as a function of wavelength, so you'll be able to use that to look at light sources and see their spectra. So one of our labs coming up is also a measuring spectra lab, where you're going to be able to go around and find different light sources and look at their spectra using this diffraction grating. Another little note on that, I'll send out an announcement about this too. Our department head asked me to send all of the Walla Walla folks their lab equipment through student mail. So if you sent me an address in Walla Walla, Reed has your lab equipment. So at some point, 10 to 4, you can go by and they should have it for you. It should be there. I sent it out Monday. If you are not in Walla Walla, it should be on the way. Hopefully it'll be there soon, but none of these labs have to be done right away. So hopefully that won't be an issue. Okay, so like I said, I think we're going to probably spend most of the rest of the class on this activity. We'll kind of see if we have some time to come back together and debrief after. But does anyone have any overall questions about spectra before you get to play a bit with why we can use spectra to identify elements? Cool. Okay, well, feel free also, as you're going through the labs, if you're looking for lab equipment, send me an email. We'll get it all sorted out. So today's activity in our assignments, it's day 8. It should be available, and there's an activity called emission spectra. So we're going to be looking at The emission spectra from hydrogen. This is another one that uses one of those NAAP labs that we used before. So you'll probably have this flash issue again. You remember if you hit that little lock button and change it to allow, and then reload the page, it should load our simulator. If you don't have a thing that says allow, and this is also in Chrome, I'll put you in breakout rooms so you can work together, so hopefully one person can get it to work. Just remember, you can go to site settings, and in site settings, one of the options is to allow Flash to work. It is also in the little NAAP lab applet. So if you downloaded that, let me just really quickly show you where that is. So if you downloaded the NAAP lab applet, it's going to be in the hydrogen energy. So when you open it in the hydrogen energy levels, it'll be the hydrogen atom simulator, which I already had open, so it's getting angry at me. So hopefully we can get a good portion of people access to this. And then we're gonna see how when we shoot light at different wavelengths at a hydrogen atom, different things will happen depending on what the wavelength of that light is. You have to be more careful. There we go. So that is your goal. Let me go ahead and open up some breakout rooms so you can work on this together. And I will bounce around to help out.